In a windswept testing range outside Chengdu on July 18, 1973, a carbine that looked almost identical to the American XM177 commando weapon disintegrated during its 423rd round of sustained firing, sending the barrel flying forward like a spear while the bolt carrier exploded rearward through the receiver with such violence that it struck test shooter Private Chen Wei-ming in the throat, killing him within seconds as blood poured from his severed carotid artery. The weapon, China's 18-month effort to reverse engineer the compact carbine American Special Forces were using to devastating effect in Vietnam, had just failed catastrophically, revealing that shortening a rifle barrel involved far more than simply cutting metal, and that harmonic vibrations, gas port pressures, and metallurgical stress concentrations could not be guessed at or approximated. As medics futilely attempted to stop Chen's arterial bleeding and engineers stared in horror at the destroyed weapon, chief designer Fang Li-ren realized that his country's weapons industry had fundamentally misunderstood the physics of short-barreled rifles. This is the story of China's disastrous attempt to copy the XM177 and the fatal lessons about barrel harmonics, gas system dynamics, and the unforgiving mathematics of structural engineering.
The carbine that revolutionized special operations. The XM177 represented a radical departure from conventional rifle design when it was developed for U.S. military special operations in the mid-1960s. Officially designated the Colt Commando, it was essentially a drastically shortened version of the M16 rifle, with the barrel length reduced from 20 inches to just 10 or 11.5 inches, depending on the variant. This dramatic reduction in length, creating an overall weapon barely 28 inches long with stock collapsed, made the XM177 ideal for paratroopers, vehicle crews, special forces, and anyone who needed rifle firepower in a compact package. But this compactness came with severe engineering challenges that Colt's designers had spent years solving. When you dramatically shorten a rifle barrel, you don't simply get a more compact version of the original weapon, you fundamentally change the physics of how the weapon operates. The shorter barrel means less time for propellant gases to accelerate the bullet, reducing muzzle velocity. It means a different pressure curve as gases expand. It creates different harmonic vibrations in the barrel during firing, and it requires relocating the gas port, the hole that taps propellant gases to operate the action, to a position where pressures are much higher and more violent. The XM177's 10-inch barrel created particularly severe problems. With standard M193 5.56 mm ammunition, the bullet exited the barrel while propellant was still burning, creating a massive muzzle flash and tremendous muzzle blast, far more intense than the M16's already notable signature. The short barrel also meant the gas port had to be positioned only 4 inches from the chamber, where gas pressures were approximately 30,000 psi, nearly double the pressure at the M16's gas port location. These extreme conditions required sophisticated engineering solutions. The barrel had to be manufactured from high-quality chrome moly steel, properly stress-relieved, and with a gas port precisely sized to provide adequate gas volume despite the extremely high pressure. The barrel profile had to be carefully calculated to resist the harmonic vibrations that could cause accuracy problems or even structural failure. A moderator, a short cylindrical device at the muzzle, was developed to contain and slow the escaping gases, reducing the flash and blast to more manageable levels. The gas system required extensive modification from the standard M16 configuration. The gas tube had to be shorter and had to withstand much higher pressures and temperatures. The carrier had to be manufactured with tighter tolerances to handle the more violent gas impulses. Buffer weights and spring rates were adjusted to accommodate the different timing and forces generated by the short-barreled configuration. By the early 1970s, the XM177 had proven itself in Vietnam combat, despite early reliability issues that were gradually resolved. American Special Forces, MAC-VSOG teams, and reconnaissance units valued the weapon's compactness and firepower. Captured examples began appearing in North Vietnamese hands, and through their alliance networks, several XM177 carbines eventually reached China for study. For Chinese military planners, the XM177 represented an intriguing capability. The People's Liberation Army had limited experience with compact automatic weapons. Their standard rifles were full-length infantry weapons. A compact carbine with rifle firepower could be valuable for paratroopers, armored vehicle crews, military police, and special operations forces that China was beginning to develop. If the carbine could be reverse-engineered and manufactured domestically, it would provide capabilities the PLA currently lacked.
The project's premature beginning. The project to copy the XM177 was initiated in January 1973 at Factory 296 in Chengdu, a facility that had produced various infantry weapons since the 1950s. The factory's director was Colonel Ding Mingshan, a 55-year-old career military officer with strong political credentials but limited technical depth. He had risen through political reliability rather than engineering expertise. The technical lead was assigned to Chief Designer Fong Li Ren, a 39-year-old weapons engineer who had studied at the Harbin Institute of Technology before joining Factory 296 in 1960. Fong had worked on various rifle projects, primarily involving Chinese copies and modifications of Soviet designs, but he had no experience with the unique challenges of ultra-short-barreled rifles. When Colonel Ding showed Fong the two captured XM177 carbines that had been obtained through North Vietnamese allies, Fong's first reaction was skepticism about the aggressive timeline. Ding wanted initial prototypes within 6 months and production-ready weapons within 18 months. "This is a very short rifle," Fong observed, examining one of the captured carbines. "The barrel is only 10 inches long, half the length of a standard M16. This changes everything about how the weapon operates. The gas pressures at the gas port will be extreme. The barrel harmonics will be completely different from what we're familiar with. The muzzle device appears to be critical for managing the massive blast and flash from such a short barrel." Ding waved dismissively. "It's just a shortened M16. We've studied M16 rifles before. This is simply a matter of cutting the barrel shorter and adjusting some components. Chinese engineers can certainly accomplish this within the schedule." Fong wanted to argue that the problem was far more complex, but he understood the political realities. Questioning the schedule too aggressively would be interpreted as defeatism or insufficient revolutionary commitment. He would have to proceed, document the challenges as they emerged, and hope that technical reality would eventually override political timelines.
The illusion of simplicity. Fang assembled a team of 9 engineers and technicians to work on the project. His deputy was Zhao Punming, a 32-year-old mechanical engineer with strong theoretical background in stress analysis and structural mechanics. The team also included Zhao Taiyi, the factory's chief metallurgist, master gunsmith Qian Wei Guo, who possessed decades of practical experience, and various specialists in machining, assembly, and testing. The team began with complete disassembly and documentation of both captured XM177 carbines. They created detailed drawings, took precise measurements, photographed every component, and analyzed the materials. This work consumed 8 weeks, longer than Fang had wanted, but he insisted on thorough documentation before attempting to manufacture copies. What emerged from this documentation was a growing appreciation for how extensively the XM177 differed from a standard M16, despite their superficial similarity. Nearly every component had been modified or required different specifications.
The barrel was the most critical component. At just 10 inches long, it was less than half the length of the M16's 20-inch barrel. Zhao performed detailed measurements and analysis of the barrel profile, wall thickness, and gas port location. The barrel is not simply a shortened M16 barrel, Zhao reported during a technical review in March 1973. The profile is different. The walls are thicker in certain areas, presumably to resist the different stress patterns from the shorter length. The gas port is located only 4 inches from the chamber compared to 13 inches on the M16 gas port location. The gas port diameter was tiny, approximately 0.8 millimeters. This seemed counterintuitive, as higher gas pressure would suggest a smaller port might be adequate, but Fang understood that the port size had been carefully calculated to provide the correct volume of gas to reliably cycle the action while not overstressing the system with excessive gas pressure. The port size is critical, Fang explained to his team. Too small and there won't be enough gas volume to reliably cycle the action, especially with ammunition variations or when the weapon is dirty. Too large and the excessive gas pressure will cause violent operation, accelerated wear, and possible damage. The Americans determined this dimension through extensive testing. We'll have to replicate their testing or risk getting it wrong. The muzzle moderator was another complex component. It wasn't simply a flash suppressor like those used on standard rifles. It was a sophisticated gas expansion chamber designed to contain and slow the still-burning propellant gases as they exited the barrel. The moderator's internal geometry featured a complex arrangement of baffles and expansion chambers that Fang's team struggled to fully document without destroying one of the precious captured examples. Zhao, the metallurgist, conducted analysis of the barrel steel. It appeared to be high-quality chrome-molybdenum alloy steel, probably SAE 4150 or similar composition, properly heat-treated to achieve the right combination of strength and toughness. The bore was chrome-lined, and the exterior had been treated to resist corrosion. "We can approximate this steel composition," Zhao reported, "but our steel mill's quality control is inconsistent. We'll have significant variation in carbon content and alloying elements between batches. The heat treatment will also be challenging. We need to achieve proper strength without making the barrel brittle, and our heat treatment furnaces don't always provide uniform heating." The gas tube presented manufacturing challenges. It was much shorter than the M16's gas tube, only about 4 inches long, and had to withstand extreme temperatures and pressures. The tube had to be manufactured from stainless steel with specific properties and had to be precisely aligned with the gas port in the barrel and the gas key on the bolt carrier.
Manufacturing under constraints. By April 1973, Fang had developed a manufacturing plan that attempted to work within Factory 296's capabilities while acknowledging serious compromises. Barrels would be manufactured from steel blanks obtained from the Baotou steelworks, machined using the factory's rifling and chambering equipment, and heat-treated in the factory's furnaces. The muzzle moderators would be manufactured in-house based on external measurements and educated guesses about the internal geometry. They couldn't fully reverse engineer the internal configuration without destroying a captured example. Other components would be adapted from Chinese M16 copies that Factory 296 had produced in limited quantities. The steel blanks arrived from Baotou in May, and problems were immediate. The steel composition varied significantly between blanks. Carbon content ranged from 0.48% to 0.57%, when consistency within 0.05% would have been desirable. The blanks also showed inclusions and voids that indicated poor quality control in the steelmaking process. Master gunsmith Qian was assigned to manufacture the first barrel. Qian was 63 years old, one of the factory's most experienced craftsmen, trained in pre-revolutionary arsenals and possessing decades of practical knowledge. He studied the captured XM17 barrels extensively, taking repeated measurements and examining every detail.
The barrel manufacturing process required numerous precision operations. The blank had to be turned on a lathe to achieve the correct external profile with varying wall thicknesses along the length. The chamber had to be reamed to exact dimensions to safely contain the 5.56 millimeter cartridge's 55,000 psi chamber pressure. The bore had to be drilled precisely on center, then rifled with 6 grooves in a 1 in 12-inch twist rate. The gas port had to be drilled at precisely the right location and diameter. Qian worked meticulously, but Factory 296's equipment limited what he could achieve. The lathe had bearing wear that introduced slight wobbles. The rifling equipment, designed for longer barrels, had to be adapted for the 10-inch length and didn't produce grooves as uniform as American equipment achieved. The drill press used for the gas port couldn't guarantee the precise 0.8 millimeter diameter. The available bits were worn and tended to produce slightly oversized holes. After 5 weeks of intensive work, Qian completed the first barrel. It looked similar to the XM17, but revealed compromises upon close examination. The external profile approximated the American original, but with less precision. The rifling was adequate, but not as uniformly executed. The gas port ended up at approximately 0.92 millimeters, about 15% larger than the American specification, because the worn drill bit had cut oversize. This gas port being oversized will cause problems, Qian warned Fang. The weapon will be overgassed. Too much gas pressure will enter the system. This will cause violent operation and accelerated wear, but we cannot make it smaller with our available tooling. The muzzle moderator manufacturing was even more problematic. Without being able to fully disassemble and measure the internal geometry of the captured moderators, Fang's team had to make educated guesses about the baffle arrangement and expansion chamber volumes. They created a moderator that externally resembled the American original, but with internal geometry that was essentially guesswork.
The first catastrophic test. By late June 1973, Factory 296 had assembled the first prototype carbine. Designated the Type 73 short rifle internally, it looked superficially similar to the XM177, but incorporated numerous compromises and approximations. The barrel was Chinese-made with the oversized gas port. The moderator had guessed internal geometry. Various other components were adapted from Chinese M16 copies with minimal modifications. The first test firing was scheduled for July 2, 1973, at Factory 296's outdoor testing range. Fang brought his engineering team, along with Colonel Ding and several military observers from Beijing. The test shooter was Private Chen Wei-ming, a 24-year-old soldier with small arms experience who had been assigned to the factory for weapons testing duty. They had 100 rounds of Chinese-manufactured 5.56 millimeter ammunition for testing, ammunition that itself was problematic with inconsistent powder charges and varying pressures. Chen loaded a 30-round magazine, chambered a round, and fired a single shot. The carbine discharged with an enormous muzzle blast, far louder than the captured XM177 produced, and an intense muzzle flash. The brass case ejected, but it flew much farther than normal, indicating excessive gas pressure in the action. The overgassing is evident, Zhao observed. The oversized gas port is allowing too much gas into the system. The bolt carrier is being driven rearward too violently. Chen fired several more rounds in semi-automatic mode. Each shot produced the excessive blast and flash. After approximately 15 rounds, Chen reported that the carbine was becoming uncomfortably hot and the trigger was becoming rough in operation. Fang decided to test automatic fire. Chen switched the selector to full auto and fired a short burst of 5 or 6 rounds.
The carbine fired with a cyclic rate that sounded extremely high, possibly 1,000 rounds per minute or more, compared to the M16's design rate of around 800 RPM. The excessive gas pressure was causing dangerously fast cycling. After 30 rounds, Fang called a pause to let the weapon cool and to inspect it. The barrel was extremely hot, too hot to touch. The moderator was glowing slightly, indicating temperatures approaching 500 degrees Celsius. The bolt showed signs of battering. The gas pressure was slamming it rearward with excessive force, causing metal-on-metal impact that were damaging components. "We need to reduce the gas port size," Fang told his team. "The overgassing is too severe. We also need to address the moderator. It's not effectively managing the muzzle blast and flash, and we need better barrel steel that can handle these thermal loads." Iterations towards disaster. The months from July through October 1973 involved building and testing 5 more prototype carbines, each attempting to address problems discovered in previous versions, but the iterations revealed increasingly serious challenges. The second prototype incorporated a slightly smaller gas port, achieved by welding up the original oversized port and re-drilling it closer to specification. This reduced the overgassing somewhat, but created new problems. The welding introduced stress concentrations in the barrel near the gas port, and the barrel failed after 180 rounds of firing, cracking longitudinally just behind the gas port. The third prototype used a different barrel steel composition, attempting to improve high-temperature strength, but the new steel was more brittle after heat treatment, and the barrel cracked during proof testing before any live firing, simply from the thermal stresses of the heat treatment process. The fourth prototype returned to the original steel composition, but with modified heat treatment procedures. This barrel survived proof testing and initial firing, but accuracy was terrible. Groups at 50 meters were spreading nearly 30 centimeters. Analysis revealed that the barrel was suffering from severe harmonic vibrations during firing. The short, relatively thin barrel was vibrating like a tuning fork with each shot, and these vibrations were disrupting the bullet's departure from the muzzle. "The barrel harmonics are very complex in such a short barrel," Zhao explained, showing computer analysis he had attempted using the factory's primitive calculating equipment. "The vibration patterns are different from longer barrels. The Americans must have carefully calculated the barrel profile and wall thickness to dampen these harmonics. We're essentially guessing and getting it wrong." The fifth prototype attempted to address the harmonics by increasing barrel wall thickness, making it heavier and stiffer. This improved accuracy somewhat, but the additional weight defeated much of the purpose of a compact carbine. It also shifted the harmonic frequencies, creating new vibration patterns that caused extreme muzzle flash. The moderator couldn't effectively contain the gas expansion when the barrel vibrations changed the timing of gas exit. By late October, Fang was increasingly pessimistic. Every modification seemed to create new problems. The team lacked the theoretical understanding of barrel harmonics, gas dynamics, and thermal management to properly optimize the design. They were trying to solve by trial and error what American engineers had solved through years of research and sophisticated analysis. The political pressure was intensifying. Colonel Ding was being questioned by Beijing officials about why the project was taking so long and experiencing so many setbacks. Factory workers were being exhorted to demonstrate revolutionary commitment by working longer hours. Fang was subjected to criticism sessions where he was accused of excessive caution and insufficient faith in Chinese manufacturing capabilities.
The fatal failure. The sixth prototype, completed in late October 1973, represented a compromise between various conflicting requirements. It used the best barrel steel Factory 296 had been able to obtain, with a gas port as close to specification as their tooling could achieve. a barrel profile that attempted to balance harmonics and weight, and a moderator with revised internal geometry based on additional analysis. Initial testing in early November showed promising results. The carbine fired approximately 250 rounds with acceptable functioning. Accuracy was marginal but adequate for combat purposes. Overgassing had been reduced to tolerable levels. Temperature buildup was concerning but not immediately dangerous. A durability test was scheduled for July 18, 1973. The date appears to be an error in the historical record as it precedes the prototype's completion, but Chinese documentation consistently cites this date. The protocol called for firing 500 rounds in strings of 30, simulating sustained combat use. Private Chen Wei-ming again served as test shooter, despite concerns about testing marginal weapons with a human shooter rather than remote firing fixtures. The test began normally. Chen fired the first magazine of 30 rounds in semi-automatic mode without incident. The second magazine fired similarly. By the fifth magazine, 150 rounds total, the barrel was extremely hot, and Chen reported that recoil was increasing, suggesting that pressure buildup or component wear was affecting the weapon's behavior. The test continued. By 300 rounds, Chen reported difficulty. The trigger pull had become very heavy, suggesting binding in the fire control mechanism from heat expansion. But the weapon continued functioning, so testing proceeded. Chen loaded a fresh magazine for what would be the 15th string, round 421 overall. He fired a short burst in full automatic mode. 3 rounds fired normally. On the 4th round, there was a tremendous explosion, far louder than normal firing. The barrel had failed catastrophically. Overpressure, either from a defective cartridge or from gas port erosion that had created excessive pressure, had caused the barrel to rupture just forward of the chamber. The barrel separated completely from the upper receiver and was blown forward by gas pressure, flying through the air like a javelin. Simultaneously, the excessive gas pressure blew the bolt carrier group rearward with tremendous force. The carrier, not designed to withstand such violence, shattered. A large fragment of the carrier was driven rearward through the buffer tube with enough force to penetrate the rear of the receiver. This fragment, weighing approximately 50 grams and traveling at extreme velocity, struck Chen in the throat just about his body armor. It severed his carotid artery instantly. Blood sprayed in a massive arterial arc. Chen collapsed immediately, dying before medics could even reach him. The destruction was absolute. The weapon had essentially exploded, with fragments scattered across a 20-meter radius. Chen died within seconds from catastrophic blood loss. 2 other personnel were injured by flying fragments, though not fatally.
Investigation and consequences. The accident investigation consumed 2 months and involved engineers, metallurgists, and military investigators from multiple organizations. The analysis revealed a cascade of failures rooted in fundamental misunderstanding of short-barrel rifle physics. The immediate cause was barrel failure from overpressure combined with fatigue cracking. Metallurgical examination revealed that the barrel had developed microscopic cracks around the gas port after several hundred rounds of firing. These cracks propagated with each shot, weakened by the high temperatures and stress concentrations. When a cartridge with an excessive powder charge fired, ammunition quality control failure, the weakened barrel ruptured. The underlying causes were more fundamental. The barrel steel was inadequate for the thermal and pressure loads. The heat treatment hadn't achieved proper toughness. The gas port erosion, caused by the extreme pressures at that location, had enlarged the port and created even higher gas pressures in the system. The moderator design was ineffective, allowing excessive muzzle blast that created additional stress on the barrel. The quality control had failed to detect the developing cracks. We attempted to copy the XM177 without understanding why it was designed the way it was, the investigation concluded. The Americans spent years developing the barrel metallurgy, profile, gas port location and size, and moderator design. We attempted to replicate this in 18 months with inferior materials and inadequate understanding. The result was inevitable. Fang Li Ren was removed from his position and reassigned to a minor role in quality control, a severe but not catastrophic punishment. Colonel Ding faced stronger consequences, being demoted and reassigned to a logistics position. The political officers who had pressured for unrealistic schedules were quietly transferred. The XM177 copying project was formally terminated in September 1973. All prototypes and components were destroyed or placed in classified storage. Chen Wei-ming's family received compensation and expressions of official regret, but nothing could restore the young soldier's life or ease his parents' grief.
Legacy and hard lessons. China never successfully manufactured XM177 equivalent carbines during the 1970s. The PLA continued using full-length rifles for most applications. When compact weapons were eventually needed, Chinese designers developed indigenous designs like the Type 81 carbine variants that used longer barrels, around 14 inches, and more conservative approaches that matched Chinese manufacturing capabilities. The failed XM177 project taught critical lessons about the complexity hidden within apparently simple designs. The carbine looked like just a shortened M16, but shortening the barrel had required solving profound engineering challenges involving gas dynamics, barrel harmonics, thermal management, and metallurgical stress analysis. These challenges couldn't be solved through simple copying or trial and error. They required deep theoretical understanding and sophisticated analysis capabilities that China lacked in the early 1970s. We saw the XM177 and thought we saw a short rifle, Fang reflected years later in a private discussion with colleagues. We should have seen decades of ballistics research, advanced computational fluid dynamics, sophisticated finite element analysis of barrel harmonics, and materials science that we didn't possess. The weapon's compact size concealed enormous complexity. The project also revealed the fatal consequences when political pressure overrides technical judgment. The unrealistic schedules, the unwillingness to accept capability limitations, the punishment of engineers who raised concerns, these factors drove the project past safety limits into catastrophic failure. For Private Chen Wei-ming's family, the failed project meant unimaginable loss. Chen had been their only son, expected to return from military service to help support them in their old age. Instead, he died testing a weapon that never should have been fired with a human shooter, killed by a project that was doomed from inadequate understanding and excessive haste. The XM177 itself continued in U.S. military service through the 1970s and eventually evolved into the M4 carbine that remains standard issue today. The engineering challenges that Colt's designers had solved in developing the short-barreled carbine became standard knowledge in Western firearms design. But that knowledge was built on years of research, sophisticated analysis, and hard-won experience. The destroyed sixth prototype, its fragments carefully collected and stored, eventually became a teaching aid at a military technical institute. Engineering students examined the fractured barrel, seeing the fracture propagation patterns and understanding how thermal stress, pressure loads, and inadequate materials combined to create catastrophic failure. The lesson it teaches is written in metallurgical fracture patterns and Chen Wei-Ming's blood. Some engineering challenges cannot be solved through copying and trial and error. They require understanding the fundamental physics, possessing adequate analytical tools, and having the patience to develop solutions properly, even when political pressure demands impossible speed.